matter of fact, but if somebody requests it, yeah, I can record it and then I can post this or send it to MayJ. The way I usually send a large file like this, because it does tend to be a large file, is on YouTube. I just post it and then send her a link as to how to view it. Okay.
Okay.
So let's get back to this third type transformation. We covered the first two, which was a vertical shift. And here, let me just label these again. This is a vertical shift. This is a horizontal shift. This is a vertical stretch or compression. This is a horizontal stretch or compression. This is a vertical reflection. And this is a horizontal reflection. Now we've gone through examples of the first two on what the new function would look like if it was shifted vertically. So let's pick up with 3. And what I've been doing, now that I got a little more room, I can draw this curve a little bit. And the original function is f of x equals 2 to the x power. And that has a point on it. Its most important point is 0, 1. And it looks a lot like this. Now, if I have a function where I stick some number in front of the function, like 3, what does that do to my elementary function? Once again, what's my elementary function become when I multiply it by 3?
Your elementary function, it becomes f of x.
No. What does this start with? Always start from left to right. I noticed that you do this a lot. You start in the middle or you start on the right side. Start on the left side. So if you look over here on the left, it starts out with a number, C. And in this case, 3 is C. So the very first thing I have to have is a 3. And it's just 3 times the function. And the function is 2 to the x. And so it's 3 times 2 to the x. Nothing complicated about it. Now, 3 times 2 to the x, what I know about that is that when x is 0, that thing is 3. It's not 0, 1. Because 2 to the 0 is 1. 3 times 1 is 1. So when I go to plot the new function, the transformed function, it looks like this. It still starts way down here like that, but it goes up much faster as you would expect. It's 3 times higher. And that represents a stretch. And so this function right there would be 3 times 2 to the x. Whereas the red function is 2 to the x without the multiplier in front. All right, let's keep going down. Now, it's not particularly easy to see on that represents a vertical stretch, but they call it a stretch for a reason. And that is that I had a point right here that vertically got moved up by a factor of 3. It was at 1 on the y-axis. Now it's at 3. Well, that sounds like a vertical stretch to me. So that's why they call it that. And that's why they say that it's a stretch in the y direction. And every point on this graph got multiplied by 3 vertically in order to get to the new one, including points over here. That point was there, and now it's way up here, 3 times further away from the x-axis, or vertically stretched by a factor of 3. Okay. Now let's talk about the horizontal stretch or compression. The last two are actually pretty easy. This is maybe the hardest one, is the horizontal. Now you'll notice in the horizontal one, the C is inside, as with all horizontal transformations, the C is inside. So an example of this might be f of, and I'll use the same number, 3 of x. And what would that be? If this is the elementary function up here, and I no longer have an x, I have a 3 of x. So what am I supposed to do with that 3 of x?
You're supposed to multiply the 3.
No, it's no multiplying, it's substituting.
With substitute?
Whenever you have something inside the parentheses, your only job is to take whatever it is and substitute it for x in the elementary function. Well, what does that get you? Substitute 3x for x.
3. It's not 3, not 3. What the fuck? Oh, like.
What if I told you to substitute 7 for x? What would it be?
7 to the x power.
No, I said substitute 7 for x.
Oh, substitute 7 for x. Oh, wow. How do I explain this? Okay, so
You had it right. You just had it backwards, Maylene.
I had it backwards.
Yeah, it's not 7 to the 2 power. It's 2 to the 7th power.
Oh.
When you substitute something for x, you just erase it and write whatever you're substituting for. So if I wanted to know what f of 7 is, it's no longer x, it's 7. So I'm going to substitute 7 for x. It's real simple. That's what substitute means. So now I want you to substitute 3x for x. What does that become? If you you start there, and instead of 2 to the x power, I want you to substitute 3x for x. So what do you get?
Okay, so you get x to the 3rd power.
Nope.
No,
I want
it's
you to substitute 3x for x.
3x. Oh, 3x for x. Okay, so I don't know how to say this. Verbalize it. I don't know how to verbalize it. I know how to write it, but I don't know how to verbalize it. 3 to the root of.
Why are you changing and sticking a 3 instead of a 2? That says 2.
Oh, that's a, oh my god.
So it's 2 to what? It's not 2 to the x. I'm substituting 3x for x. So what is it?
X. You're substituting 3x for x, so it's be 3x.
There you go.
3x, yes.
So it's 2 to the 3x. You need to be able to verbalize it, because if you can't verbalize it, you can't be thinking about it right.
Okay.
Okay, so verbalization is a really big thing. So remember how to verbalize these.
Okay.
It's you start with the base, and then after you say 2, you say what the exponent is. So it's 2 to the 3x power. All right, let's graph that one. Again, I'm going to start with the elementary function that goes through this point, 0, 1. Looks just like the other red lines that I've drawn. Only now it's 2 to the 3x. And if we look at this information in the column that I'm pointing to here, if the number is greater than 1, it compresses it in the x direction. Well, this number is greater than 1, it's 3. And what they mean by compressing it is, picture this red line as a piece of a wire or string, and you're going to push on it in that direction. That's what compressing in the x direction means. And if you think about it, if you raise the number 2 to the 3x, it's got to go up a lot quicker than 2 to the x, right? Because 2 to the x, that's 2 and then 4. Whereas 2 to the 3x, that becomes 2 cubed, and then 2 to the 6th, and then 2 to the 9th, goes up much faster. So its growth rate is much faster. However, when x is 0, it still goes through that exact same point, because 2 to the 3x is 2 to the 0, which is still 1. So it doesn't change that point. What it does is it makes it go up much faster, really compresses it a lot. And that's what a horizontal compression means. A horizontal compression is very much like a vertical stretch. Notice that up here, that was a vertical stretch. Or excuse me, that was a vertical, yeah, that was a vertical stretch. This graph goes with this one here. So that was a vertical stretch. This is a horizontal compression, but both of them are similar in that the blue curve goes up quicker than the red curve does.
Oh, yeah.
There is a difference in the vertical stretch. This key point, 0, 1, actually moved up to 0, 3. And it doesn't go anywhere when I have a horizontal compression, but the shape of the curve does similar stuff. It goes up quicker. All right, we got 9 minutes to cover the last two, and that's good because they're the easiest ones. I'm going to erase that for the moment. For one thing, you will be getting a recording of this, and you'll be able to view whatever I've written on here. But let's talk about, I'm going to draw a line here so that I have room to do the two bottom ones. Again, everything is based on this elementary function, 2 to the x power. So if I put a negative sign in front of the x, or in front of the f of x, what does that do to my elementary function? Verbalizing.
Okay, let's do. So it reflects about the.
No, well, no, I don't want you to tell me that. I want you to tell me what the new function is.
Okay, the new function.
Instead of 2 to the x, what is it when I stick a negative sign in front?
A negative 2 to the x.
Very good. It's not hard. Yeah, you're making it far harder than it is before. It's simple, really. In other words, you take your basic function and you stick a negative sign in front of it. Now, what that is going to do, again, I'm going to plot the parent function. And what does it say about a negative sign that is a vertical reflection? It says it reflects about the x-axis. And the reason I call that a vertical reflection is because if you put your hand above the x-axis and flop it over vertically, it makes that curve look like this. That is a vertical reflection. You see why that is a reflection about the x-axis?
Yeah, I see why.
Yeah, in other words, this point is now 0, minus 1. And every point on here, if that point were 5, 7, then this point down here would be 5, negative 7. It is a mirror image, as long as, no, I don't want to call it a mirror image. That's confusing, actually. It's a reflection. That's what reflections are. Okay? And the final one is if the negative sign is inside the function, what is that going to look like? That's not quite as obvious. But again, use the rule, whatever is inside the parentheses, substitute for x in your elementary function, which is 2 to the x. So what does it become?
That it becomes.
What does f of minus x become? If f of x is 2 to the x.
A 2 to the negative x.
Good. Finally, you're getting it. All right. Now, if I draw the original function, 2 to the x, it looks like this. And I want to, that means it's a reflection about the y-axis, right? That's what it says. If it's inside, if it's a horizontal reflection, now take your hand, cover up the first quadrant and flip it to the left. That's what we're going to be looking at. And that's why I call it a horizontal reflection. And if I draw it in blue, it looks like that. Notice that that point didn't change because it got reflected about the y-axis, and so it was on the y-axis, it didn't go anywhere. But this point over here went to there. An equal distance from the x, or the x coordinate, is the same distance. That's what happens when you reflect across the y-axis, is that these distances are the same as that distance. Okay.
Okay.
And that is transformations in a nutshell. I don't know how to explain it any better than that, which is good because we're just about out of time. The only thing that I would do to go forward on this, and if we have another session for tomorrow, we can probably work on that, would be to give you a bunch of functions.
Yeah, we have 2 sessions tomorrow.
Okay, good. We can continue this. But what I'm going to do is I'm going to give her a bunch of functions like x plus 2 and say, what is that? Well, that is a vertical shift. Or I'm going to give her 2x. What is that? That is a vertical stretch. Or I'm going to say, what is x minus 2 in parentheses? That's a horizontal shift to the right. So I'm just going to start making up functions and letting her figure out what each one of them is, because you have to be able to do that to be able to pull off the transformation. Now, the ones I just drew in blue, those are all linear. And like I said, those aren't really very good for talking about transformations. So I'm going to stick with the exponential theme tomorrow. And what I'm going to do is stuff like this. What is that? What is that?
This.
Is that horizontal or vertical?
Which one?
Yeah.
So,
If I say g of x is a transformation of f of x, and it looks like 2 to the x minus 2 power in parentheses, not that I need the parentheses, but just for clarification. What is that?
it's horizontal.
Okay, good. And if I added a +4, what is the +4?
It's a shift.
I need the direction.
Oh, it shifts.
Vertical or horizontal?
Oh, it's vertical.
Because it's outside the function. That's inside the function. That's the difference. And so I'm going to give you a bunch of functions and ask you to tell me whether that, what that function, what that adjustment does. Does it vertically shift it? And if so, which way, up or down? Does it horizontally shift it? If so, which way, left or right? So forth or so on. Okay. All right. We've got 2-hour-long sessions scheduled for tomorrow.
Correct.
Yes.
Okay.
Earlier. They're
Okay,
earlier.
good. That's helpful to Mei Lee. I notice she is yawning a
Tired.
lot tonight,
Mhm.
which is natural since it's 9 o'clock there. It's 10 o'clock there now. So the earlier, the better,
Mhm.
for purposes of being alert. Let me just check tomorrow. And it looks like they're at 2:30 and 5. Okay.
So
Now, this moving to half-hour sessions,
Mhm.
you've got a bunch of them scheduled, like you got a bunch of hour sessions scheduled for the next week.
Yeah, because I tried to get them as early, but some spots were
No.
taken. Mhm.
There's 2 reasons I want to go to half-hour sessions. For one thing, it works better for Zoom.
Mhm.
And another, I think it works better for Mei Lee. I do. I honestly do. So what we'll plan on doing is we'll break these up into 2 half-hour sessions with 5 minutes in between.
Okay, sounds good.
Until we run out of hour-long sessions. We'll just do it that way.
Okay.
When you get to a point where you're going to start scheduling new ones, go ahead and schedule them for half hour.
Okay. Sounds
Okay?
good. Okay.
Okay. Dokes. I will talk to you tomorrow at 2:30 my time.
Okay. Bye. Thank you.
All right. You're welcome.
bye.
Bye-bye.
Good night.
Bye.